Greetings and welcome, friends. Today we are talking about the concept of verifying trigonometric identities. Okay, so far our experience with trig identities, we've disproven some using a counterexample. But today I want to prove new trig identities, and the way we're going to do that is through showing that the two things I'm equating, right, the two expressions that I'm saying are equal. Actually finding a way through some sort of manipulation with previously known trig identities, manipulating them in such a way that I end up actually showing that the left side was equal to the right side all along. So suggestions for this process of doing this are going to be some of the following. And it takes a little while to get into the habit of this. It might be similar to when we did, I didn't do it with you guys, but proving concepts in geometry where you had two-column proofs. The skill is going to be in knowing all of your tool set, knowing things like your trig identities, knowing how to perhaps factor, or knowing some of your patterns for factoring or expanding things. And just kind of rearranging things in such a way that you could prove that the left side is equal to the right side. So here's some suggestions. You probably won't have time to write all these down, so don't worry about it. They're also found on page 431 of your text. It says, and these aren't actually numbered in your text, but that's fine. So one general approach might be transform the more complicated side of the equation into the simpler side. All right? And as far as transforming it, you could say that's simplifying, right? And we just did some problems like that on last night's quest. So that's one way you could do it. Another way is substitute one or more basic trig identities to simplify expressions. All right, so also like last night's quest, if I have a Pythag identity that I can swap out with something else, or a reciprocal identity, or a quotient identity, I'm going to use those back and forth as it makes sense. If rearranging that's going to allow me to get something simpler. 3, this one's where some of our algebra skills are going to come into play. You might want to factor to simplify, or sometimes maybe even multiply. Okay, and then a fourth option is multiply expressions by an expression equal to 1. And this is specifically usually going to occur when we have some form of fractions occurring. Is often when that would be helpful. And then the last one, we saw this show up on last night's quest as well, was express all trigonometric functions in terms of sine and cosine. That's the nice thing about them, is all of them can be rewritten as those. So sometimes by getting it all written in terms of just two of our trig functions, we might be able to better see what's going on in the situation. So let's do an example, and actually I think I've got a handful of examples here, and I'll show you what we've got going here. And we're just going to pick away at these over time and try to get better at them. And that's the sort of thing it takes, is just a little bit of practice. A little bit of practice. And eventually, hopefully, we'll be more comfortable with it. So let's say, for our example, I want to verify the following. I'm claiming that this is a trigonometric identity. Okay? That's my claim. So in order to do so, I'm going to have to prove that this left-hand side is equal to the right-hand side. That's what I'm going to have to prove. So let's do that. So let's see. In this case, I've got secant squared x minus tan x times cotan x is equal to tan squared x. Now, I'm realizing that these two guys, I think I can do some work with that right there. Because tan x and cotan x are reciprocals of one another. So the first thing I'm going to do is use a recip identity. And I think I can rewrite cotan x, right? So cotan x is equal to 1 over tanx, right? Bam. So I will get secant squared x minus tanx times 1 over, no, I just wrote tax there, I forget the n, multiplied by 1 over tanx is equal to tanx squared. So what happens now that I've got this? How is this beneficial to me? Yeah, tan x and tan x cancel each other out. So now I'm left with, I guess I don't Need that equal sign there. So now I have secant squared x minus 1. Is that equal to tan squared x? And I'm seeing, well, actually, there's a couple ways to do this. Notice, so far I've worked on the left-hand side. I could keep working on the left-hand side, but I can also rearrange things the other way as well, whichever way happens to make sense. So I could have, do a little work over here, do a little work over here, and as long as they somehow meet in the middle, being equal to one another, I've proved it. Okay, so you don't have to solely work on one side or another. But either way, I think both of these are leading me to the same thought. I see a tan squared, I see a secant squared. I'm thinking, what do you guys think I'm thinking? Pythagorean. I see some squares here. I'm definitely thinking about some Pythag identities, right? So what is our Pythag identity that relates sine squared? Or, sorry, secant squared.
Tan squared theta plus 1 equals sec squared theta.
Tan squared theta.
Sec. I said sec.
Plus 1 is equal to sec squared theta. Yep. And now I've got some options here. Notice it doesn't quite fit perfectly. Although, well, actually, you could modify this. Or maybe I might just realize, hey, secant squared theta is equal to this whole thing. Whether you want to modify it slightly or just replace this portion of it, you could. It's all up to you. There's like probably 3 or 4 different ways you could move from this point, but we're definitely on the right track. So let's say I do this replacement. Okay, so I'm going to have secant squared theta is the same as tan squared plus 1, and I'll have to use x's in this case. So tan squared x plus 1 minus 1, is that equal to tan squared x? And I think you guys can probably see what happens from here. Plus 1 minus 1 cancel out. I get tan squared equals tan squared. And I've proven it. All right, cha-ching, it works. So that means that this is in fact a trigonometric identity. I've just proven it. All right, it's a brand new one. It's a unique one. It's true all the time for all values of x.
Would it be ethical to just add 1 there and move it to the other side?
Yep. You could have added 1 here if you wanted to get that, to look more similar to that. A bunch of different ways. You could have subtracted 1 here and used a modified Pythag, or yeah, all sorts of things you could do. And it's okay whichever way you perceive it is fine with me. And what I want to point out is this is not the answer. Okay, so don't box that. The answer was the entire process. All right, this was a proof that I did. It was my justification, line by line, obeying the laws of math until I came to a conclusion that was true. The whole thing is the answer. Okay, so it's not just like, oh, the answer is tan squared x. That's not what that means. All right. So let's try another one. Let's see. And paste this in here. My fraction showed up a little bit sad. Copying it from my Google Doc. This says 1 plus tan squared all over cosecant x equals tanks. Huh. All right. So, what is your guys' first thought on this? I kind of like this numerator here. I think we can do some work with that, doing some replacement.
Isn't that just like 1? Oh.
Let's see, what's the Pythag identity there? Tan squared x plus 1 equals secant squared x, or thetas, depending on what it is, right? So it looks like, well, 1 plus tan squared is the same as tan squared plus 1, so I think that numerator I can just replace, right, with secant squared x, if I'm not mistaken. So this is going to be the same as secant squared x over cosecant x secant x equals tanks. All right, now what do you think I can do? Yeah, this guy cancels out with one of the ones up top. So I'm going to have secant x over cosecant x equals tanks is my claim. Huh. Now, secant x and cosecant x, I don't necessarily have a direct path to relate that to tan x, but I think I'm going to rewrite both of those as their reciprocals. I'll double recipit. So I'll change that one and that one at the same time. Right, I happen to know that secant x is equal to 1 over cosx, and cosecant x is equal to 1 over sinx. Right? So I'm just going to double substitute right there. So 1 over cosx all over 1 over sinx. Okay. And what do you guys think I should do from here? I get a stack of frac. Multiply by the reciprocal of the denominator. Oh, guys, we're getting warmer here. Multiply across. Oh, yeah. What's the identity I'm using here? Quotient, right? Which says pretty much exactly what I have right there. And just to point out, I technically could replace the right-hand side with this, or I could replace the left-hand side with this. All right, so that's what I just want to point out, that I technically have some options here. All right, and I get tanks equals tanks. What do you know? What do you know? So, friendly friends, let's take a look at another problem here. Let's see. Let me take a snapshot. Verify the following. I'm excited about this stuff. Like I said, we're spending 2 days on this, so here we go. So I'm just trying to fit as many examples in as I can, and then have you guys try some with partners, hopefully. So this is 7 sinx plus 5 cosx all over sinx cosx equals 7 secs plus 5 cosec. Wow. Craziness. Now, when I'm looking at this, I'm seeing there's actually a couple ways you could do this. And that's often the case. I'm seeing a lot of sines and cosines. I'm thinking, let's just rewrite the other two as sines and cosines. All right, this is an example where that might be helpful. So I'm going to double recip, right, where secs is equal to 1 over cosx, and where cosec is equal to 1 over sinx. Right, I think if we just double substitute here, have it all written in terms of sine and cosine, it might put us a little bit warmer in seeing what we could do here, perhaps. So 7 sinx plus 5 cosx all over sinx cosx equals, I could rewrite this as 7 over cosx, right, for this part here, or 7 times this guy is the same as 7 over that, plus 5 over sinx. And I actually have a few options now. I see a bunch of fractions with almost common denominators. I could combine these two fractions. Or I could find the LCD of all sides and multiply both sides by it and see what that does for me. And either way is actually going to give you the answer. So what is the LCD here? Just sinx cosx, right? So what do you guys think? Do you want to multiply both sides, or do you want to just combine these two fractions? Combine them. Let's do that. So I'll multiply this by coscs over coscs, and this one by sincs over sincs. Equals, my left-hand side's staying the same for a while, so I'm just going to throw some ditto marks in there to save us some work. And let's see, plus 5 coscs over sincs coscs. And sure, I could cancel this out and this out, but I just added those in intentionally, so I already know that these are unreduced fractions. But what's nice about the fact that they have the same denominator now? Yeah, I can add the numerators. And that gives me the left-hand side, so we're done. Right? So, yeah, so that's interesting. You also could have done this problem by separating this plus sign into two fractions over the same denominator and cancel stuff out. And it kind of would have been doing like this whole process backwards is what it would have done. But yeah, so lots of different strategies. But the main idea I want to show you is just that like start picking at these things, like start changing things and see if it helps, see if there's anything that you recognize that could be good sort of idea. All right, one last example. Let's grab a little snapshot of this guy. Bam. There we are. So verify sine of A. So I used A this time. Sometimes it'll be alpha, sometimes it'll be X, sometimes it'll be theta, all right, so it could be all sorts of letters for the angles.
That helps so much because I always get confused when I see that. I'm like, oh god, what do I have to do now?
Yeah, it's just, yeah, different name for the same thing, that's all. So sine A over cosec A plus cos A over sec A equals cos squared A minus cotan squared A. Huh. Let's see, I never thought of using this route on this problem. What's that? Huh. Well, I just realized you could maybe use some Pythag identity stuff in here. You could. And that would be fine. I think I'm going to instead work with reciprocal identities for these guys and see what happens. All right, but more than one way to do this problem. Feel free if you want, you know, take a snapshot off of YouTube and record your own YouTube video of you doing it another way and post it on YouTube as a reply video to me. That's fine. I won't be upset. I might even like it. Might maybe add a comment like, hey, nice work there with your trig identities. Right? Who knows? Take it away. You know what I'm saying? So let's see. Let's use some recips. Cosecant A is going to equal 1 over sine A. And, ooh, this one is interesting. Secant A is going to equal 1 over cos A. Yeah, so I guess, yeah, if you're talented enough, I mean, I'm plugging in 1 over sine A here. I could just straight up multiply by the reciprocal if you want. If you're brave. You guys think you can do that? Okay, all right, I'll write it all out. I'll write it all out. Here we go. Plus cos A over 1 over cos A. Yep. Oh, we might still have to use the Pythag one after. Well, we'll see, we'll see. Well, I'm not, because I'm anticipating I might do some more work here, I'm not going to rewrite this side. This might be one where I work on the left and the right and then meet in the middle. But let's just keep working on the left and see where it leads us. So yeah, dividing by a fraction is the same as multiplying by its reciprocal. is what Amber was saying there. So that's sine A times sine A over 1 plus cos A times cos A over 1. Which, what's sine A times sine A? Sine squared A plus cos squared A. Cos squared A. That sounds like Spanish or something. Sine squared A plus cos squared A? That should be familiar. That's just straight up Pythag. That's equal to 1. Okay, I think I've simplified this left-hand side pretty good. Let's see if I can simplify the right-hand side. So cosecant and cotan, and I've got squares in it. Let's see what a Pythag looks like for that. What's our Pythag say? 1 plus cotan squared theta is equal to cosecant squared theta. How could I get this to look like that? Or I could just replace the cosecant part with this and then see what happens. In that case, the cotans would cancel out. Yeah, let's do that. That sounds fun. More than one way to do this. 1 plus cotan squared A minus cotan squared A. Right, so I've just replaced that whole thing. And notice that the cotan squared A's cancel out. And then 1, 1, 1, cha-ching. Verified, friends. Verified. So, best of luck doing this stuff on tonight's quest. It's just going to be like a little bit of a, tweaking and rearranging and see what you can do. Not all the times is writing everything in terms of sine and cosine helpful, but it might be. And keep an eye out for those squareds. Usually it suggests that a Pythag is hiding somewhere in its midst. All right, have a great day, Internet friends. Bye-bye.